Hello, good morning, everyone, and welcome back. This week, we have covered lectures on how to apply machine learning models on predictions and finding correlations between data sets. In the IT tutorial, we'll be applying the concept that we have learned from the lecture and see how that can be realized in a coding environment. So please come to the folders of this week. So I'll be using online Jupyter Lab, which will be very similar to the one you're using. So please visit this week's folder, Urban Statistic and Machine Learning. And under the folder, there are the following files and data sets, existing data sets. So in here, there are this set of Berlin data for training and the Berlin trained models and Berlin trained model best. So I'm just going to go over about the contents of each folders. So currently we only need the contents of the Berlin data for training. So if we go here, there are two files in here. One is Berlin continuous and the Berlin categories. So if we open the file called Berlin continuous, it contains the following contents. So this is a file. Some of them will be looks quite familiar to you. So ID, file ID or JPEG ID, they should be the same, longitude, latitude, representing the location of the contents in the street view images. There are something that you don't recognize, like for example, from Q1, Q2, all the way to Q8. However, there will be also elements that you do recognize. So hypothetically, by now we have already done a tutorial on image segmentation, image classification or instance detection. So those are the elements from image segmentation. For example, percentage of the sky, percentage of trees, and etc. from each of the images that is sampled. And there are the ones that we see is indeed the count. So CT represents the count, like count of person, count of bicycles, and the count of cars in each of the thing. So those are the contents that come from the, let's say, the image segmentation and instance detection. So what are those elements, the Q1 and Q8? Those are the numbers that come from subjective rating. What is subjective rating? So I'm just going to show this one. Perhaps you have seen this kind of survey very similar to this case, this kind of comparative survey. It asks you to compare two things against each other and ask for the contribution. Ask for your opinion on a certain topic. So at the end of the day, this kind of survey will generate this kind of statistic outcome. I mean, we can download this one into a CSV, but in this survey, it only contains two questions. One is the work from home score, and another is work from office score. So and those are our Q numbers representing quality numbers. However, in the Excel file here, those Q numbers represent output from a similar type of survey that we conducted with students in 2020 and 2001 that we can just simply use its outcome. So basically, the question we ask the students to compare, the only information we give them are the street view files, and we ask them questions such as which of the things, left or right, has a better quality in terms of spatial orders. Which one of the things seems like there are better access? Which one of the things are better in terms of aesthetic qualities? which one of the thing looks better in ecological qualities, which one is looks better in for its enclosure, which one is looks better in terms of thing richness, and which one is better in terms of scale. So by applying the Microsoft True Scale method in statistic, we're able to generate a score, like a quality score for each of the categories for each of the image sampled at this location. So what does our exercise do? This exercise, so once we understand the contents of the statistic files that we got from Urban Survey, the goal of this exercise is to build a model that we're able to map the qualities, the spatial statistic numbers, such as the percentage of the walls, percentage of the trees, to this kind of quality numbers, and see which are the most important influential factors for each of the qualities. With a similar method, we can insert any outcome of statistic here and build such a model. For example, we can use those kind of street statistical numbers, the street thing segmentation numbers, to pretend, for example, in case of this and this survey, like the score of living preference from work from home or work from office, and finding what are the primary coefficient influencing factors of spatial qualities to each of the decision-making process. And the reason that there are two sets is that one is it represents two modes of statistic. So for the category numbers, instead of giving it a continuous scores, we're asking the student to rate them in terms of number level 0 to 5. So in the category scales, it represents a full number, while in the continuous scales, we're asking them to compare and thus generates a numerical output. So this just that there are two data sets that represents two surveying process. In this case, we will be using the continuous numbers for better performance. Now go back to our home folder and open this one. So there are two codes here this week. One is called training your first machine learning model to make the prediction. Another one is predict with your pre-trained machine model. That means we can train our models based on a statistic data set we collect on Berlin first, and use such data sets to make predictions about other cities or other street view images. For example, districts in Berlin that we have never seen before, for Hong Kong, Brisbane, or New York space. Because this is the powerfulness of machine learning models, that where you can train it on a data set and apply it on things that we have never seen before. So first of all, let's start with the training process. So double click and let's open this file. So in this case, we does use a few, let's say, libraries that may or may not installed. So if you encounter any library non-installed issues, please run this, and you only need to run these ones. So hypothetically, if we run this, it will check if we have already installed them, and the warning is fine, don't worry about it. So it looks like it's all installed. It doesn't have any red warnings. So first of all, we have to load the data set for training and identify what is our input X set and what is our output Y. So first of all, read Berlin training data, and it has 300 data sets, 46 columns, 46 categories. And here are the index of all the columns. So we have the longitude, ID, longitude, latitude, Q numbers, the counts, and the image segmentation results. Now we have to locate what are the subjective quality scores that we try to predict. So what is our output Y? What is our goal for prediction? And I have introduced here a few line of code for segmenting the contents. So you can, so if there is a comma here and on the left comma, it represents a row number, like the range of the row number we try to sample, and on the left, we represent the row of the column number that we try to extract with our code. So for example, this line says, and we're going to keep, so without any number means we're going to keep everything, we're going to keep our rows. However, we're going to extract column between column number 5 to column number 13. So I'm just going to run this. Okay, it looks all right. So this is the outcome. So Q1 is the type. It's actually like a space type that we get from GIS, like it's residential or commercial or etc. So we won't be predicting that. We'll be using the code to predicting the orderliness, accessibilities, aesthetic, ecologies, enclosure, and richness and scales of each set. So those are our output label Y. Second of all, we have to extract what are our input labels. So of course, we can use our input labels to make prediction. However, if we're looking at them, some of them may be, let's say, less relevant, such as counts of the traffic lights or signboards, sidewalk, and etc. So there are two ways to do it. One is to keep every features, and one is to keep the predominant features. The risk of keeping every features is that not everything exists in our testing, in our evaluation set. So in this case, and in addition, for the input of our model and for the input of our other city to make prediction, they have to have the same input categories. So we can't training a model that contains an input on sidewalk, but the sidewalk doesn't exist in our prediction, doesn't exist in the city we're trying to predict in. For example, if we train a model in, let's say, Brisbane, in Xi'an, then it's, or in a inner land city in China, that it will probably doesn't have any like categories on river, and applying on Brisbane may have become problematic, or vice versa. Like a model is trained on Brisbane to make prediction with water in it and apply it to an inland city that doesn't have water, it will cause modeling errors. So it's just more convenient for us to identify the features that we will be used to make prediction on in the order of the features. So this is quite important. Feel free to just pick the features that are common in the biggest common denominators in your training data sets and your prediction goals. So in this case, we're using it to prediction on the Hong Kong site. Yeah, and in the Hong Kong site, because at least in this data sets, as an example, I only had the image segmentation result, so I don't have the instance detection result. So I will be only making predictions from the outcome of image segmentation, which means the percentage of the sidewalk, percentage of trees, without any information on the counts, like how many trees are the thing and how many people are the thing. So we will be only using these columns. All right. So with this line of the code, we're actually able to separate those columns for all of our sampling points in the Berlin dataset. So we're still working on the Berlin dataset to train the model. Now, our goal of this exercise is to predict those Q scores based on those percentage numbers of the elements in the same. In this case, we can apply these models to any scenarios in other parts of the world, such as Hong Kong in our case. So you don't really need to be able to write this code, but what basically this part of its code means. Remember we had mentioned that the machine learning models, the traditional machine learning models are quite lightweight to train. And a lot of the students has problem of picking out which one is the most effective ways of identifying the relationship between the elements. So in this part of the model, it's basically we'll be training nearly all of the existing models types in scikit-learn library. So if you look there, there are the training of random forest, there are the training of support vector machines, training of the nearest neighbors. So those names look very familiar. And the process is that it will, from the going through the columns one by one, going from the one by one, they're going to fit each set of the data into our training process. So the column is the quality of space. So those are the Q1, Q2 to Q8. So those are the column of quality predictions. And we will be using training Berlin training models and save them in this file. So I hypothetically, if you open this one, there should be currently no model in it. The X is our values and the Y is our quality score at each values. So it should be very similar. It should be those. So DFF. Yeah, DFF are our values, DFQ are our qualities. The next step, which looks very familiar, is basically to separate them into our test set and training set, and the split is 0.20. With the 20 test set being at 20% of the entire data to validate the performance of our model. The rest is just to reformat our data to the right structure that you don't really need to worry about. Next of all, we're from scikit-learn library import different regressors. And of course, you can also visit the scikit-learn library. I'm seeing if I'm having this library link here, but if not, you can just make a search on scikit-learn or just search sklearn. It will show you the link to the library. 1 second. Here. So the machine learning in Python in here, that you will have a good direction to all of the models. So install user guide. It shows the linear models, kernel models, and etc. Unsupervised learning, Gaussian mixture. So it has all the models that it contains in here. So we'll be using some of the popular ones. So basically, it's also identified that it will put the file into the tag. Tag represents the name of the model, the name of the file plus the model KNN into the folder location that we have identified. So as a result, it will have a lot all the trained models saved in our trained model folder with the tag, text represents the quality 1, model KNN, and etc. So this is KNN. We also have a support vector machine, random forest, decision tree, linear regressions, Gaussian process, voting selections, ADA boosting regressions, and the Bayesian regressors. So we're training all those models at once and trying to find the best model that suits our prediction process. Now, that find the best model that can describe our the relationship within the data sets. Okay, so just wait a second. Now the training has started. So as the training progresses, let's read what does it say. So let's just ignore the type ones. So for Q2, it means the prediction of the order. It represents so the R2, so RMSE, MAE represents the accurateness of each of the model and the performance of each model. For those of you who doesn't remember what each represents, I have included the one here. So R2 is called R, it represents R square. It's a square value from 0 to 1 and can commonly state as a percentage. As R square of 100 means all changes in the subtracting ratings can be explained by the change in the features. RMSE, root mean squares, is a standard deviation of the residues. It tells how do you concentrate the data around the line of best fit. So in this case, we want the R square to be as big as possible. Normally, we do need the R square of like 40% or 50% to say the model is effective. And we want our RMSE to be as small as possible, to have as less error as possible. So just looking at them, the prediction of the type is quite accurate. However, if you look at the R square of our prediction of the order, it's a bit problematic. So basically you can tell what type of space from the image set. However, the prediction of the error, it's there are only, let's say, maximum 14% of the change can be described to the image itself. So the correlation is not that strong for interim, but there are still correlations, so no worries. You can still use it to make predictions, but it's just that the output may not be that accurate. The excess, the maximum is R square is about 18, so slightly better. So R square represent how well the changes in the data set is described by your by our input. So for you, just going to sketch here. So if for something with the higher R square, so if R square is 1, then if you're doing a linear regression, that means that all the points can be described by our regression line. However, if the R square is close to 0, it means that, yes, we can still fit a line here, but the points could be something like that. So the changes in the board, even though we find a best fit point, but the changes in the data may not actually be quite relevant to this. So that's what R square means. So first of all, we're checking which models fits our criteria. So normally we need around 40% or 50% to identify a valid model. So if we look at the ecological scores, okay, so I think ecological scores of performance is better. So this one is the R square is almost 38%, and the error is only there 17% for our Gaussian regressors. I say, okay, we're going to take this one. For ecological scores, for enclosure scores, there is actually quite significant correlations. For example, a lot of them are over 50s, and a lot of them, the mean square errors, mean average errors, for example, the voting selection seems like our best fit. Like Gaussian's regressor is also working, but I would say this one, the working selection, is our best models for predicting the ecological quality of the thing. In terms of the richness, so it's quite subjective. It seems like the reviewer or the one who are making the selections comparisons cannot make up their mind consistently. So the best fit is only about like 12% or so. So I wouldn't use the outcome for the richness. Last but not least, scale is also fine. So I think for the scale, the SVM is the best one that making the prediction. It means like 34% of the qualities that can be explained by the change in the data sets. So in this case, we'll be using the SVM for predicting qualities. This is the voting selection for predicting enclosure. Our decision tree. And the voting selection or the bagging process for predicting ecologies. Probably we won't predict aesthetic. It seems like it's quite subjective. And perhaps just for demonstration, we can also use this one to predict the access. And I don't think there are any values in predicting the orders because obviously like the R square is quite low in all of them. So in this case, there are the trained models. So please find them in the trained models. So for example, here it is the one which we're using. We're using the SVM for Q8. It starts with 0, so Q8 is actually 7. So SVM and the Q1 is actually start from the tag 0. So Q8 is SVM support vector machine. Precision tree Gaussian linear. Yeah, support vector machine. Let's copy this one and put this one in our trained model best. Some process, okay, so it's fine. So I think in the trained model best, I have been using the Gaussian models, which is very similar to in terms of outcome between the Gaussian models to Bayesian regression. So in the trained model area, there are 3 models that I have already selected in this process. The Gaussian models, the number 5 is Gaussian process. Yep, so this one should have the best performance. And for number 4, it's a voting selection. Yep, this one. Not number 4, so number 4 is actually number 5. This one, voting selection. And the 5 represents quality 6 is Gaussian process. Yeah, this one. So those are the models that I have selected and put them in the best trained models that we will be using to make predictions for our future data sets in the future data things. So feel free to choose your own models. So those are all the models we have created and download them and re-upload them into the model training best part. So those are our select models for best performance. And of course, normally we do save the scores. So this is scores of all the like different tags from model 0 to 7 quality Q1 to Q8 and all the like statistic and performance of each models. So I normally save this next to the trained model. I think it's in here. So example model selection. And in this way, we can read and understand what is the performance for each of the models. So once we close this one and then we save it on our hard drive, we don't need to retrain them to check their performance. We already know the performance that is saved in their save folder. Okay. Last but not the least, it's about checking the importance of the features for each of the models. Now we have all those features here. Another thing we want to have a look is what are the features that are most important to our outcome, to the changes in our outcome. For example, what kind of spatial features are important in determining ecology or enclosure and etc. So in this case, first of all, we just need to open the model we're using. So there are two ways to do it. First of all, that we use a random forest model that by itself, it comes with this kind of feature importance function. So please just pick a random forest model from our birding trained model datasets. And here are some the process about data formatting, how to export tree scores, how to print them, and etc. But essentially, the only thing that we did is to generate, you see, parameter updates, and updates the feature importance and plot them down here. So basically, you just need to run that. And this is the outcome. This is the rank of feature importance. So if we're looking at number 2 and going back to our original birding models, number 2 is actually Q3 because it starts with 0. So what is Q3? Q3 is access. So for evaluating the access, sky and buildings are the most important factors that influence our decisions and perceptions on the accessibilities of the street. That was pretty obvious, followed by the quality or quantity of plants, trees, earth, and road. So basically the vertical elements and the horizontal elements in our model are the most influential on our evaluation of whether the thing looks very accessible or not. Similarly, we can check about other features. In Berlin, so this is an ecological score, so it's number 5. So I think in here it will be 4. So let's check what are the most important contribution factors for our to evaluating ecology. So just simply change it from the 2 to 4. So I'm just going to rerun it. Obviously, it's trees. Trees are by far the most significant factors that contribute to our perception of the ecologies in the thing. So in this case, without knowing any background information about psychologies or urban planning, the machine learning models is able to identify the elements that are most important to our concept perceptions and how important that element is. It will be important tools that help guide our decisions. Let's see what are other things we can be looking at. So richness or scale. Let's try scale. So what are the most important factors that contribute to our scale? Sense of scale. Sorry, it should be 7. It's a sky. That's a percentage of the sky. So in another word, I think it represents like it's influenced by the height of the building and the narrowness of the street. But the percentage of the skies is the most important factors that influence our perception of the scale in a setting. Feel free to play around with it and play around it with different data. Second of all, I'm going to introduce another tool here to visualize the relationship, different from the other previous one. So this part is using the probability models to find statistic correlations in the data set. So it doesn't really need any machine learning model. So this one will not re-emphasize, it will not be using any of the model here. The only thing it will use is an Excel sheet. So this is a very important graph, and like a correlation matrix heat map is an important tool that you can apply with minimum coding ability. Basically, you only need to give it an Excel sheet, and it's able to find correlation heat maps between all the columns. First of all, let's import data. And in this case, I'm using the Berlin data for training continuous. So this is our original ones. Maybe I'll use the categories just to demonstrate that we don't really need to train anything. Let's see, name. So remember, we did not use the category file for training, but I'm just going to showcase it. That even though we did not train any models, we can still use this tool. That basically very simple. It identifies what are the qualities that we try to identify. We try to find correlation, and basically it will generate this heat map. So basically, deep blue represents the highest correlation, positive correlation, and the deep red represents the biggest negative correlation. So what is a positive correlation? Positive correlation means, for example, let's say number of trees and the ecological values. So means maybe more trees there are, the better sense of ecology there are. So that's positive correlation. While the negative correlation is sketch here. Which example I'm probably safe of safety. And the lighting quality. So wait, this one. Let's say the sense of the residential, preference for residential, and the cars on the road. So probably, especially in Brisbane, like it's possible that the more cars it is on the thing, the less residential or less preferred residential areas it is. So this is a negative correlation. Means when the feature grows, the preference, the one you're trying to evaluate, actually decrease. So that's a positive and negative correlation. In this case, it's actually represented here. So now with a closer look at this one, we can save it in our own folders and download it. So obviously for example, for our orders or scales there. So this one, of course, it's 100% correlate to itself. But what are the other positive correlations? Sense of scale is very positively correlated to the sense of enclosure and the sense of richness, of course. And it's also positively correlated to the percentage of building, percentage of plants, percentage of trees, sidewalks, and etc. It's negatively correlated to the percentage of sky and the roads. So the more sky it is, the less sense of the scale there are, as rated by our reviews. And also, let's take a look at our ecology score. So ecology is here. It's mild positively correlated to the richness. It's negatively correlated to the richness. It's significantly positively correlated to the tree. It's positively correlated to the grass and negatively correlated to the building as well. And for example, in here, this is enclosure. So it's strongly negatively correlated to our sky parameters. So this heat map will give you a very good identification about the correlations between all the static outcomes and the feature values here. Even though it cannot build a model to make predictions on future street scenes, but it will give you some support for your urban design argument, like why you want to engage certain elements. And now this is a lot for this week, and please place around it and feel free to insert your own Excel files. It can be any Excel files in here and trying to see what the heat maps reveals in terms of data correlations. In the next tutorial, we'll be following up with the prediction with a pre-trained model and see how our trained predictions can be applied in other contexts.